Is visible to everybody? Somebody please confirm.
Yes, sir.
Okay, so we will begin now. So today we are going to start with the new topic, that is a rectangular element. Okay, so let us quickly begin. So for example, we have a coordinate system which is like this. Okay, so on this side you have x, and on this side you have y. Okay, so in the rectangular element, the as the name suggests, the shape of this particular element is a rectangular, and the nodal connectivity which is assumed in this particular element is always in the anticlockwise direction, same as the nodal connectivity at the constant strain triangular element. Okay, so there are four nodes over here. So this will be called as node number 1, this will be node number 2, this will be node number 3, and this will be node number 4. Okay, so this rectangular element has got four nodes, and every node has got a deformation in u direction as well as in the v direction. So u direction deformation is parallel to the x-axis, and v directional deformation is parallel to the y-axis. Okay, what is assumed over here is something like this. So if I take a straight line, or which is a line which is exactly dividing the uh, element into two equal parts. So let me draw a straight line here. Okay, so if this is equal parts, so in that case the length of the element, okay, is considered as twice a. Okay, so the distance between node number 1 and node number 2 is twice a, whereas the height of this element is considered as twice b. Okay, so half of the side, that is half portion, is called as b, so the total height will be called as twice b. Okay, so this is what is assumed just before the derivation of the stiffness matrix. Okay, now since there are four nodes, so every node is having possible displacement in x direction and y direction. Therefore the u matrix, okay, so this is your u matrix. So u matrix now will be having 8 components. Okay, one is the u1 and v1, that is the horizontal and vertical deformation at node 1. Similarly, then there will be u2 and v2, so horizontal and vertical deformation in the node 2. Then we have u3 and v3, similarly u4 and v4. Okay, so these are the possible deformations in the element. So your the unknown vectors for this particular element will be 8. Okay, so 4 horizontal deformations and 4 vertical deformations. Okay, so now let us quickly see the derivation of the stiffness matrix for the rectangular element. Okay, now remember, while deriving any shape functions or maybe a stiffness matrix for any element, first of all we need to assume the displacement function. Okay, so now there are two possible displacement. One displacement is there in x direction, and second displacement is there in the y direction. Okay, so earlier what we have assumed, that u is nothing but the deformation in the x direction. So if you remember, in the CST element we have assumed a deformation or the displacement polynomial something like a1 plus a2 into x plus a3 into y. This is what we have assumed in the CST. Okay, that is constant strain triangular element. But this is a rectangular element, it has got four nodes, so we have to consider one more component component over here. So this will be a4 into x into y. Okay, so since there are four nodes, we have to consider the polynomial which is something like this. Okay, similarly we have to assume a certain displacement polynomial for the deformation in the vertical direction also. So in the vertical direction we are assuming the similar polynomial. Only thing is, now I am assuming this as a5 plus a6 into x plus a7 into y plus a8 into x and y. Okay, so the last function will be dependent on x as well as dependent on the y. Okay, so now our objective over here is to find out the values of a1, a2, a3, a4, and a5, a6, a7, and a8. Okay, so now for the time being, let us consider only the deformation along the u, that is along the x-axis only. Okay, so now what I'm going to do over here is, first of all, let me write down the nodal coordinates. So this node 1 will be having coordinates something like x1, y1. The node 2 will be having coordinates x2 and y2. This will be having coordinate something like x3 and y3, and here we have x4 and y4. Okay, similarly, if you want to show the deformations, so here you have something like u1, and here you have v1. Here you will be having u2, and here you will be having v2. Okay, because see, I am taking the deformations which are parallel and in the direction of the positive axis only. Okay, so here you have u3, and here you have v3, and lastly here you have u4, and vertically you have v4. Okay, u4 and v4. Okay, so this is what is the element which is looks like this. Okay, so now the very first thing what we have to do is we have to find out the unknowns, that is a1, a2, a3, and a4. Right now I am focusing only on the u part. Okay, that is the deformation along the x-axis. Okay, so now for this purpose, what I'm going to do is I'm going to apply the boundary conditions. Okay, so let me write down over here. So I'm just saying that is apply boundary conditions. Okay, so if I apply the boundary condition, what is going to happen? So let us say at node 1. Okay, so at node 1, u will be called as u1. Okay, x will be called as x1, and y will be called as y1. Okay, so just for sake of simplicity, let us call this as expression a. Okay, so if this is the case, in that case your expression a, how it will look like? It will look like something like u1 equals to a1, sorry, plus a2 into x1 plus a3 into, you will have now y1 plus a4 into x1 y1. Okay, so on the similar lines we can have another boundary condition, that is at node 2, u will be something like u2, x will be something like x2, and y will be something like y2. So your expression a will look something like this. So u2, because u will be replaced by now u2, so this will be a1 plus a2 into x2 plus a3 into y2 plus a4 into x2 and y2. Okay, so similarly we can write the same thing for node 3 and node 4. So this expression a for node 2, sorry, node 3 and node 4, it will be something like this. So this will be y3 will be a1 plus a2 into, now this will be x3, a3 into this y3 plus a4 into x3 and y3. On the similar lines, u4 will be something like a1 plus a2 into x4 plus a3 into y4 plus a4 into x4 and y4. Okay, so these are the four equations we can get by substituting the boundary condition. So this is expression 1, this is expression 2, this is expression 3, and this will be your expression 4. Okay, so now what we can do is we can combine these four expressions. So I am just combining equation 1 to equation 4. Okay, so if I combine all these four expressions, so what I'm going to get, I'll be getting something like u1, u2, u3, and u4. Okay, So this I am just combining over here, and here what I am going to get is something like this. So this is 1, you will get x1, you will get y1, and here you are going to get x1 and y1. Okay, here you will be getting 1, this will be x2, y2, x2, y2. Here this will be 1, this will be x3, y3, x3 and y3, and lastly we have 1, x4, y4, x4 and y4 multiplied by, now you will have something like a1, a2, a3 and a4. Okay, so now if you multiply the first row with the first column, you are going to get expression number 1. The second row and second column, you are going second row and first column, you are going to get the expression number 2. Okay, so what I have done, I have just combined these expression in form of a simple matrix. Okay, so now what I'm going to do here is I'm just going to represent the similar thing in a short form. Okay, so let us call this is vector u. Okay, I'm saying vector u over here. This will be something like matrix x. Okay, multiplied by, you have vector a. Okay, so I'm just representing the same thing in a very small format. Okay, so because this I'll be using in the further calculations, right? So now what was our expression a? So you can see your expression a was like this. Okay, so let me write down this expression a at the bottom one more time. So so my expression a, so my expression a was something like, it was u equals to a1 plus a2 into x plus a3 into y plus a4 into x and y. Okay, so this is x and y. Okay, so what I am going to do over here is I am going to rewrite this expression a in a different form. Okay, so let me rewrite this expression. So this expression a, this can be written as something like this. Okay, so this will be something like 1, this will be x, this will be y, and this will be x and y multiplied by, now you will have a1, a2, a3 and a4. Okay, so this is just, I'm just rewriting expression number a, that is the displacement polynomial, which is u. Okay, so out of which I don't know what are the values of a1, a2 and a3 and a4. So what I am going to do, I am going to use this expression. Okay, I'm going to use this expression. So this expression, I already know that u is a product of matrix x into a, where a is nothing but your a1, a2, a3 and a4, right? So I can use this particular expression, and from this expression I can get the value of small a. Okay, so small a now can be written as the inverse of matrix x multiplied by your u vector. Okay, I can write this, there is no issue in this one. Okay, so the same a value now I am going to write down over here. Okay, so here I am just going to write down this a value. So finally your u expression, okay, this u expression will become something like 1 x y, and this is xy. Okay, multiplied by this a1, a2, a3, a4 is nothing but the inverse of this matrix multiplied by your u vector. Okay, so now if I expand this, right, so let me expand this for you. So you have 1, we have x, we have y, we have x and y multiplied by, you have a big matrix over here. Okay, because this is a 4 by 4 matrix. So here you can see this is the inverse of this x matrix, and this is your x matrix, isn't it? So this x matrix is 4 by 4 matrix, so definitely its inverse will be also a 4 by 4 matrix. So I am not writing down the values over here, I'm just putting a cross symbols over here. Okay, so this will be a 4 by 4 matrix, something like this. Okay, multiplied by, okay, multiplied by, you will have this u matrix. Okay, and what is your u matrix? U matrix is nothing but u1, u2, u3 and u4. Okay, fine. So this is how the u or the displacement polynomial u can be written like this. Okay, so if you see, this matrix is one row multiplied by four column. So if you multiply these two matrices, okay, so what you are going to get, you are going to get a simple matrix which is of size 1 by 4. So this u expression, that is displacement polynomial, now will be a matrix which is having one row and four columns multiplied by, you have the same matrix, that is u1, u2, u3 and u4. Okay, so the first element, the element which is located over here, so this element will be the product of this vector multiplied by this vector, isn't it? So if you do this calculation, so what you are going to get, you are going to get some value. So these values are called as n1, the second value will be called as n2, the third value will be called as n3, and the fourth value will be called as n4. Okay, so the values of n1, n2, n3, n4, so let us say a value of n1. Okay, so let me write down the value of n1. So this n1 is a product of this row and this column. Okay, so I am directly writing down the value of n1 over here. So n1 value, it comes out to be uh, something like, in bracket, this is a minus x, then b minus y divided by, you have 4 times a and b. So similarly you have n2 also. So n2 can be written something like a plus x, this is b minus y divided by 4 times a and b. Then n3 can be written as a plus x, okay, b minus y, sorry, b plus y, not minus y, divided by 4 times a and b. And n4 will be something like a minus x, okay, then b plus y divided by 4 times a and b. Okay, so these are nothing but shape functions. Okay, so we have already seen a shape functions, so you can see these are the values of shape function. So now you can understand that now the u, okay, so this is nothing but a displacement polynomial. So this displacement polynomial, now it is depending on the local displacements. Okay, so local displacement, or you can say even a nodal displacement. So it is totally depending on what is the value of deformation in x direction at node 1 or at node 2 or at node 3 or at node 4. So it is totally depending on u1, u2, u3 and u4. And when we have assumed this, so what we have assumed, it we have assumed this as u equals to a1 plus a2x plus a3y plus a4 times x and y. So initially we have assumed that it is depending on the coordinates of the point, but now it is depending on the your nodal displacements. Okay, so now let us quickly see how the shape function is going to vary. Okay, so for example, if I draw a rectangle, okay, so let me draw a rectangle over here. I think should be like this. Okay, so for example, this will be my node 1, this will be node 2, this will be node 3 and this will be node 4. Okay, so if you talk about your n1, okay, so at node 1 the value of x, okay, so the value of x, so you just remember that this particular element has got a width of this, that is what I can say, the width is basically twice a. Okay, so what you can do is you can substitute these values over here in this particular expression, and then you can get the values of your deformation or the variation of the shape function. So whatever value of x is there, okay, so let us say if your joint coordinate is starting from here, okay, so if it is starting from here, then definitely the value of x will be 0 and value of y will be 0. So accordingly you are going to get a variation. So here the variation will look something like this. So here the value of shape function will be 1, but the value of shape function at the other nodes, it will be always 0. Okay, so it will look something like this. Okay, so this type of variation we have also seen in the CST element also. So similarly, we can have a variation of N2 as well. Okay, so let me draw a variation of N2 also. Okay, so the variation of N2 will look like this. So this will be, say, node 1, this will be node 2, node 3, and node 4. So at node 2, the value of N2 will be 1, okay, but at other nodes it will be always 0. Okay, so the variation will look something like this. Similarly, if you talk about the N3 variation, so your N3 variation at node 3, it will be 1, but at other nodes it will be 0. Okay, so it will look something like this. And lastly, the value of N4, sorry, I should draw it in this color. So the value of N4 at the node 4, it will be 1, but at other nodes it will be 0. Okay, so these four figures, it shows this is the variation of N1, this is the variation of N2, this is the variation of N3, and this is the variation of N4. Okay, so this is how the uh, shape functions are going to get vary. Okay, now coming to the most important part, that is the B matrix, that is the strain displacement matrix. Okay, so generally this is a 2D problem. Okay, okay, so for 2D problem we have two three things, like we have like epsilon x is there, epsilon y is there, and we have gamma xy. Okay, in case of axisymmetry case, we will be also having this epsilon theta. Okay, so generally what we write here, so epsilon x is nothing but du by dx, this is what we write. Epsilon y is nothing but dv by dy, and gamma xy is nothing but du by dy plus dv by dx. Okay, this is what we are going to write. Now we have already calculated the value of u. Okay, so u is nothing but something like n1, n2, n3, and n4 multiplied by, you have u1, u2, u3, and u4, isn't it? So now you can simply write it in form of an equation. So in general, what we can write, you can write u equals to n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. Okay, now if I want to calculate epsilon x, okay, so epsilon x is nothing but du by dx. So what you have to write over here, that is d by dx of, now you will have n1 u1 plus n2 u2 plus n3 u3 plus n4 and u4, right? So now let us talk about only the first term. Okay, so I'm talking about the first term over here, that is d by dx of n1 and u1. So if I talk about this, so d by dx of n1, because n1 is a term which is having the term of x and y both. Okay, so here I am just writing d by dx of n1. So n1 we have already written over here, so n1 is nothing but a minus x b minus y divided by 4 times ab, isn't it? So I'm just going to write down a minus x, then we have b minus y divided by 4 times ab. Okay, so now if you go for the derivative of this, so what we are going to get is 1 upon 4 times ab outside. Okay, then if it is d by dx, then this will be common. Okay, so you will be having something like, this is b minus y. Okay, so this will be outside. Then we have something like d by dx of a, and then d by dx of minus 1. So d by dx of minus x is nothing but your 1. So what you are going to end up with this is something like this, that is minus 1 upon 4 times AB into B minus Y. Okay, so now here B is nothing but the height of the element divided by 2, isn't it? So similarly, you can talk about the second term also. So this is the second term. So second term will be nothing but d by dx of n2. So if you write this as d by dx of n2, so here what you are going to get is something like this. So here you will be ending up with something like 1 divided by 4 times AB multiplied by, you will have B minus Y. Okay. On similar lines, you can also calculate d by dx of n3 and d by dx of n4. Okay. So d by dx of n3, it is coming out to be 1 upon 4 times AB multiplied by b plus y, and here 1 upon 4 times ab multiplied by minus of, this is b plus this is y. Okay, okay, I think this is y. Okay, so now in short, what you are going to end up with something like this. So your epsilon x, okay, epsilon x, so I'm just taking out this common, that is 1 upon 4 times ab. Okay, so this into, okay, into, you have the first term. So the first term will be something like minus of b minus y. Okay, then we have the second term. So second term is nothing but b minus y, this will be positive, and the third term will be something like, this is b plus y. Okay, and the last term is nothing but minus of b plus y. Okay, multiplied by, now you will have u1, u2, u3 and u4, right? So this is how you can get this strain in the x direction, right? Now if you observe carefully, let me go back at the top. So now what we have assumed, that we have assumed the value of u as something like a1, a2 x plus a3y and a4 this one. So now the similar type of displacement polynomial we have assumed over here also for v also. Okay, so in this entire expression, in this entire expression, u will be replaced by v, otherwise rest of the elements they will remain same, that is a1 will be replaced by a5. Okay, then something like a2 will be replaced by something like a6. Okay, and so on. Okay, so ultimately what is going to happen is we are going to end up with the same thing. Okay, everything is going to remain same, and as a result of this, what you will have, you will have a expression something like this one, that is v. Okay, that is v equals to, you will have something like n1, n2, n3 and n4 multiplied by, you will have now v1, v2, v3 and v4. Okay, same thing is going to happen. But now if you want to calculate the value of strain in y direction, okay, so let me write down the strain in y direction. So the strain in y direction will be nothing but dv by dy. So here also similar kind of expression will come into picture. So dv by dy, if you go for that, so this will be something like 1 upon 4 times ab multiplied by this entire term. Okay, so this entire matrix will come over here. Only thing is, no, I think this will be slightly different, sorry for that. You will have a different matrix over here, right? So here you will have this is minus of a minus x. Okay, then secondly this is minus of a plus x. Okay, then we have something like a plus x. Okay, and lastly we have something like a minus x. Okay, multiplied by, now you will have v1, v2, v3 and v4. Okay, so like this you can have the variations, right? So on the similar lines, we can also go for the shear strain also. So shear strain, that is gamma xy, will be calculated as du by dy plus dv by dx. Okay, so here also you will get some different term. Okay, but here you will be getting one row and 8 columns, and multiplied by, you will be having u term as well as v term. Okay, because u term is over here and v term is also over here. Okay, so you will have something like u1 v1 something like this, and u4 and v4 something like this. Okay, so as a result of this, finally what you are going to get is something like this one, that is epsilon, that is the strain component, will be having three components, that is epsilon x, epsilon y, and gamma xy. Okay, so you will end up with something like this, 4 times a and b, and here you will have a very big matrix. Okay, so this matrix will be derived from these expressions. Okay, so for example, this is your expression number 1. Okay, this will be your expression number 2. Okay, and you will also have a shear component also, this will be expression number 3. Okay, so let me write down for you. So this is something like minus b minus y 0, this will be 0, this is minus of a minus x, so this is again minus of a minus x, this is minus of b minus y. Okay, so this is the first part. Okay, then we have b minus y, then we have 0, here also it is 0, so this is minus of a plus x, again this is minus of a plus x, and this is b minus y. Okay, so this is the second component. Then we have something like b plus y. Okay, this will be 0, this will be 0, this will be a plus x. Okay, here also this is a plus x. Okay, and we have b plus y. Okay, and lastly we have negative b plus y, we have a 0 over here, 0 over here, and this is a minus x. Okay, again this will be a minus x, and this is negative b plus y. Okay, so this completes the matrix, and this will be multiplied by something like u1 v1, u2 v2, u3 v3, and then u4 and v4. Okay, so it's a big matrix, right? So in short, if you see this side we have a strain. Okay, and this side we have a displacement. Okay, so this particular matrix is now called as B matrix. Okay, so B matrix is nothing but what? Your strain and displacement matrix. So it is relating the strain with the displacement component. Okay, is it understood to everybody? Are there any queries in the derivation part? Yes, students, are there any queries?
No, sir.
Shall I?
No,
Okay, I'm
sir.
continuing now. Yes, I'm continuing now. So you see, if you remember, in the CST element, the expression of this B matrix was very much similar, isn't it? But only thing is, if you refer the coefficients which are there in this matrix, let us say this coefficient, okay, or maybe this coefficient. In the CST element, there was no term of y or there was no term of x. Okay, लेकिन इस particular expression में we do have the terms of x and we also have the terms of y. Okay, so in the earlier it was not at all there. That's why the strain was constant within the element. But in this particular case, the strain is not constant within the element. It is depending on what is the value of x and what is the value of y. Okay, so this will be very much useful for us when we want to have a variation of stresses or strain within the element. Okay, so in CST it was constant. Here in this case it is not at all constant. So for example, if you know these values, okay, so for example these values, that is u1 v1 u2 v2, they are known to you. Okay, so let me take a simple example. So let me draw a simple box. Okay, so now you know the deformations which are happening in this particular box. So let us say the deformed shape of this box is something like this. Okay, so this means you know the deformations and it is going to deform like this. So if you want to know what is the deformation at this point or what are the strains at this point, so all you have to do is you already know these values. Okay, so deformations are already known to you. So in this particular B matrix, okay, in this B matrix, you just substitute the values of x1. So for example, this is your x3 and y3. So in this matrix, you just substitute what, x3 and y3 in place of wherever there is a x and wherever there is a y. So as a result of this, you will end up with a B matrix, and if you multiply this with this deformation, so you are going to get what? You are going to get the sigma epsilon x, then epsilon y and gamma xy at what? Node 3. Okay, so at any point wherever you want to have the strains, all you have to do is just substitute the values of x and y in this particular B matrix, multiply with the deformation matrix, and you will get the values of strains. Okay, so this was not possible in the CST element, because in the CST element the variation was not at all there, the strains are constant. That's why it was called as strain displacement matrix. Okay, but this dependability of x and y on the strain is going to create a lot of trouble. Okay, why I am saying this is because once you know the B matrix, okay, so B matrix is known, what we have to do at the end, we have to generate the stiffness matrix. Okay, and our stiffness matrix K elemental is nothing but integration over the volume. We have B transpose into D into B over dV. Okay, so now you just imagine what is going to happen. So you are this, I'm just talking about this matrix part. Okay, I'm just talking about this. So if I take a B transpose matrix, my B transpose matrix will look something like this. Okay, because you see it is having the 3 rows and 8 columns. Okay, so we have 3 rows, so 3 rows will become 3 columns over here, and this is 1 2 3 4 5 6 7 and 8. Okay, so like this we have 1 2 3 4 5 6 and 7, 1 2 3 4 5 6 and 7. Okay, then we have a D matrix. Okay, so generally if you talk about plane stress case or plane strain case, it is a 3 by 3 matrix, isn't it? In case of axisymmetric problems, we have a 4 by 4 matrix. Okay, so this will be something like this, and then we have again the B value. So 1 2 and 3, so this is 1 2 3 4 5 6 7 and 8. Okay, so it will be something like this. So your matrix is matrix calculation will be a sort of trouble. Okay, so this is 8 rows and 3 matrix, and these are 3 rows and 8 columns. Okay, so if you multiply all these 3, okay, so if you multiply this, what you are going to get is a term which is having 8 by 8 matrix. Okay, the issue is not 8 by 8 matrix, the issue is the integration part, because this entire term, so this K elemental will be something like integration over the volume. Here you will have a 8 by 8 matrix. Okay, and this will be dV. So dV is nothing but the thickness multiplied by integration over the area. But now area calculation is not that simple, because your area is integrated along the length and along the height also. So in this particular case, you will have K elemental, so thickness will come out over here, and here you will have to integrate for two integration. So one is integration along the x, and second is the integration along the y. Okay, so you will have a 8 by 8 matrix. Okay, and you will have, now this will be dx and you will be having a dy. So this is the double integration part. And if you see only first component, so I'm talking about this component. Okay, so here also I'm talking about this component. How you are going to get this component? By multiplying these two matrices, or rather these three matrices. This is matrix number 1, matrix number 2 and matrix number 3. Remember this term, that is B1 term. Okay, so B1 term is having equation something like B minus y. Okay, so it is now depending on the value of y. Okay, So this is also depending on y, so this is depending on y. Okay, this is also depending on y. So what you will have, you will have to integrate all 8 by 8, that is 64 terms for dx as well as for dy. It's a very cumbersome task, okay, and it is literally time consuming, and there are possibility of many mistakes. So if you want to solve this problem manually, it is, I'm saying it is possible, but it's very time consuming, and it may create or it may attract many errors over here. Okay, so remember, you have to integrate how many terms? K11, K12, like that up to K 8 row and 8 columns. So total 64 terms you have to integrate, and you have to integrate along the x as well as along the y. Okay, so this is a very very big task, and there is no standard equation for this one. So it's very very time consuming, so it is not at all possible. Okay, so just to avoid this integration part, what we can do, we can change the coordinate system itself. Okay, right now we are working in the Cartesian coordinate system. Okay, so I'm writing Cartesian coordinate system. Okay, so because this Cartesian coordinate system is basically this one, that is x and y. Okay, so this coordinate system is creating a lot of trouble, because if you go with x and y, you will end up with a very big matrix. Okay, so just to avoid this, so what we can do, we can use the natural coordinate system. Okay, okay, so in the natural coordinate system, we have something like xi, and we also have in the z direction as eta. Okay, so how to use this natural coordinate system for any type of element, maybe a 1D element or maybe 2D element, that we will cover in the coming classes. Okay, so for the time being, just understand how the matrix is generated for a rectangular element, and it is really difficult because we have to go for double integration of 64 terms. Okay, so I hope you have understood this. Are there any queries? Yes, students, are there any queries, please? I'm stopping the recording now.